Whoops. Okay, so no Joseph or Tyler at this point. And let me go back to the first slide. There we go. Okay, we are going to start talking more about energy. We saw our first introduction to energy in lab on Monday. And so today we're going to talk about work and kinetic energy and potential energy. We'll get all of these things covered. And so we start with kind of review of what we learned in lab. In lab, we learned that work is a force accompanied with motion. And it's not just accompanied with motion. That motion has to be parallel to the force. If it's perpendicular, then you have no work. That was all covered in lab. Something we did not talk about was the units of work. If you take the unit of force, that's a Newton. The units of distance, that's a meter. So the units of work are Newton meters. And to make life simpler, we have a single unit, the joule. So 1 joule is equal to 1 Newton times meter. So when we talk about energy, we'll talk about it in units of joules. And we're going to have a whole bunch of clicker questions coming up real soon, just so you have those out. The aspect I said, only forces parallel to motion can do work. A force perpendicular to motion won't do work. So remember my examples from lab. If I had a mass here and I walked at a constant horizontal speed, the work I did was 0 because my force was upward, but the motion was horizontal perpendicular. Whereas if I took the weight and lifted it like this, then I did a positive work if I raised it, and I did a negative work if I brought it back down. Why was it a negative work when I brought it back down? Because I was going down and... Okay, gravity was pulling down, so gravity was doing a positive work. My force was pushing up. So my force was up and the motion was down, so I did negative work. Okay, so now let's... one more thing before we get to the questions. I think it's just one more. Power. Power is very simply the rate at which work is done. So rate means how much per time. So power is simply the work per time. So you could take as an example, if you are going up a flight of stairs. If you go up that flight of stairs and it takes you 10 seconds, then the power you exerted was your weight multiplied by the distance you moved parallel to the... Okay, let me back up. If you're going up the stairs, so here you are, what forces are acting on you? Okay, gravity, and that points downward. What else? Force normal, and that acts upward. Now, when you start talking about this, it gets confusing when you talk about the work, because those are the two forces acting on you. And so if you are going to go up, which of those forces made you go up? Yeah, it's going to have to be the normal force that made you go up. So you'd say, normal force did a work on me. But if you talk about how much work you did, because we know it's tiring to walk up the stairs, right? So if we talk about how much work you did, then you say, okay, so what were you putting forces on? Right? That's what you have to ask for how much work you did. So let me change colors here. What were you putting a force on? Okay, what direction? Well, you were pushing down on the stairs. And I'm going to call that force of the legs, because the legs are pushing down the stairs. And so that's an equal and opposite force to the force normal. There is another force that you are applying that you never think of. What's that other force? You what? Yeah, you were pulling the earth up as well. Right, so you also have the force pulling the earth up. Force pulling earth up. Or I could just put gravity like you said. I'll put a capital G just so it's not the same symbol. Now, which one of those is tiring you out? Well, I would say it's the force of your legs pushing that's tiring you out. Right? You can be lying in your bathtub or in your bed. You're pulling the earth up, but that's not tiring you out. So it's the force of the legs that is the one that's going to be tiring you out. And so your legs, when you're climbing the stairs, think about this. You put your leg on the step, and then you push down, and the normal force pushes up. And it's the normal force that lifts you, but you had to push down and raise your body in the process. So it turns out that the work you did is going to be the same as the work done by the normal force. And so in the end, how big is the normal force if you're just moving at a constant speed? I know it's impossible to just move at a constant speed gliding up those stairs. But if you're moving at constant speed, so acceleration was constantly zero, how big would the normal force be? If we are in equilibrium, equilibrium means equal forces. That's why LB is the pound symbol. Whoops, I put L for librium. If we're in equilibrium, the sum of the forces is equal to mass times acceleration is 0. And so that would say force normal minus force gravity equals 0. So force normal equals force gravity. And then since force of the legs is an equal and opposite force to the force normal, then that's also equal to the force of the legs. So your legs are putting a force equal to your weight downward if you're moving at constant velocity. And then you go up a distance, and so the total work would be equal to the total distance you rise times your weight. There's no time involved for that total work, right? It's just how much you weigh times the total height. Now, you might think about this. Let's say that Daisy and I decide that we're going to race from the basement of the Dick building to the top of the Dick building. So we start at the bottom, we run up those stairs. When we get to the top, how does the work I did compare to the work Daisy did? I do more work. I do at least twice as much work because my weight is at least twice as high as hers, and we went the same distance. I do definitely weigh twice as much as you at least. Not even a question there if that's what you're thinking. So it's a lot more work for me to go up the stairs. Remember that when you see me huffing and puffing, okay? The fact that I'm obese makes it more work. The fact that I'm out of shape just adds to the problem. Okay, so back to the original situation. So let's say it takes you 10 seconds to go up one flight of stairs. Then the power you had to exert is the total work, your force of gravity, times the distance you went up, divided by the time of 10 seconds. Now let's say instead of taking 10 seconds, you take a minute, 60 seconds. How does the work vary if you take 6 times longer? I'm going with Rachel. It's the same work, because the work was just the force times the distance parallel to that force. It doesn't have the time in it. But then we have the power. If it takes me 6 times longer, how does the power compare? You have less power. It's 1/6 the power. Now, when we talk about being tired, like huffing and puffing, which one is that measuring? How much work you did or the power? It's the power. It's how quickly you were doing that work. So if Daisy and I do this race to the top and she just barely beats me, well, she wins the race and she gets the glory. But if you think about it, I had to put out a lot more power than she did, even though she she beat me, because I had a lot more work that I did in just a little bit less time. And of course, in athletics, things like this, nobody talks about them very much, but they're very important. You know, something like horse racing. They care very much how much it weighs, the horse and the jockey. And if the jockey is too light, they put extra weight on the horse so that the horses all have to do the same amount of work in running around the track. And that way, they have to have the same, you know, the one that wins is going to be the one that can maintain the highest average power through the race. Okay, now I think we have a set of clicker questions, like 5 of them. So, question number 1. Not yet open. There we go. A string is used to pull a wooden block across the floor without accelerating the block. So acceleration is 0. The string makes an angle to the horizontal as shown here. Does the force applied via the string do work on the block? So this is, yes, it does work, no, it does no work, or only part of the force does work, or you can't tell. All right, everyone's answered. 2, 5, 2. Now, the fact is, there are 2 possible correct answers. So I want you to talk among the people around you to determine which one is incorrect of the 3 that people answered. And then we'll repoll it. Okay, it looks like people have come to conclusions. So let's try this again. See if we move toward right or toward wrong. We move toward wrong. What's the question you have to ask to determine if work is done? There's 2, 3 things.
Is it going to distance?
Is it going distance?
And if it's parallel
To
the force.
to the force. Those are the 2 things. So we look at this. Is it moving? Yay or nay?
Yes.
Yes, it's moving. Is it moving parallel to the force?
You could argue maybe.
Okay, the force has a piece of the force that goes this way and a piece of the force that goes that way. We can break it up into its components. And part of the force is parallel to the motion. So the 2 answers that I would have considered correct were A, yes, it does work, or C, only part of it does work, because it's only the part that's parallel to the motion that does work. The part that's perpendicular does none. So the force doesn't have to be parallel. It has to have part of the force is parallel. So if the force had been like this, well, then it would have done no work. But as long as it has a portion that's forward, it'll do work. What if the force had been like this?
Yes.
It would have done some negative work. Okay, next question. You can't answer for another 3 seconds or so, but okay, you can now answer. If there's a frictional force opposing the motion of the block, does the frictional force do work on the block? So the block is still moving just like we talked about, still pulling with that same force, but there's a frictional force. The fact is there had to be a frictional force for the acceleration to be 0. No frictional force, it would have been speeding up. Okay, this time we did far, far better. Yes, the frictional force does work. Is it a positive work or a negative work? It's a negative work. How do we come to this? We know it has distance. That was our first question. The second one is there a force parallel to that? Well, what direction is the frictional force if it's moving to the right? So we're going to have the force of friction like that. That force of friction is what we call anti-parallel to the motion. It's exactly the opposite direction, which means that the work done by that is just going to be minus the force of friction times the distance it travels. So it does a work, but it's a negative work. Okay, next question. I actually had more questions when I first wrote this, and I decided to take some out, just in case you're curious about why we have so many, because I thought that they were good for learning. Does the normal force on the floor pushing upward on the block do any work? Because obviously there has to be an upward normal force or it'll fall through the floor. I should have hit stop earlier. People were changing their answer incorrectly. What direction? Okay, we've established it's moving. What direction is the normal force? So we have this force normal pushing up. How much of this is parallel to the distance? None. Hence, what's the correct answer? No. The normal force does no work because the force, while it's there and there is distance, they're perpendicular to each other. In that case, there's no work. Okay, next to last question. A force of 50 newtons is used to drag a crate 4 meters across the floor. Now we have numbers. Notice that 50 newton force is broken into components for you. So that 50 newton force is 40 newtons horizontal and 30 newtons vertically. Now some people might say, but 40 plus 30 is not 50. That's because they're not the same direction. You use the Pythagorean theorem, 30 squared plus 40 squared is 50 squared. So we have the force broken up, and it says, what is the work done by the horizontal component of the force if it slides 4 meters? Okay. The first 7 people to answer all agreed that it was 160 joules. The last 2 had the 200. Nobody knows the order that people answered, so I'm not giving anything away. But that should give you some idea about confidence. The more confident people all said 160 here. The less confident went with 200. How did you calculate this? The correct answer is the 160. How did you calculate this, someone who got 160? Okay, you took the work is equal to the force times the distance parallel to that force, or the force parallel times the distance. You said, well, what force is parallel to the 4 meter distance? The 40 newtons. So that was 40 newtons times 4 meters equals 160 newtons times meters, or 160 joules. That make sense? Okay, let's go one further. Let's ask about the vertical force. I forgot to advance this one. How much work is done by the vertical force for the same problem? Okay. This time we ended up we have a slight majority that said 0. Back to our questions. Each time you're asked this question, you need to go back to just the two basic things. Does it move? Yes. Is the vertical force parallel to that motion? No. Uh-oh. What does that mean? No work. So the correct answer was no work. Now, what's the total work done? This is the question I took out. At least I trust I took it out. What's the total work done by this force? You have to blurt it out. It's going to be 160 joules because it was 160 joules by the horizontal part, 0 joules by the vertical part. 0 plus 160 is 160. So that I figured that was not a very useful question to ask. We could probably all figure out that sum. Now we're going to shift to another type of energy. Actually, I said another type of energy. We haven't talked about energy yet, have we? Not in particular. So, we have talked about work. Work is a force with something moving because of that force. A definition of work is a change in energy. So energy has to do with work. So if you look at that, if a definition of work is the change in energy, then they must have the same units. And kinetic energy is energy something has because it's moving. So if I'm stationary, I'm not moving, I have no kinetic energy. Kinetic means in motion. But if I'm moving, if I'm strolling along, doing my strut, then because I have motion, I have some energy. So there's energy involved, and I had to have some work to make me move, to get that energy. What provided the work? What single force did the work that made me start moving? Same as the force that makes a car go. Friction. So when you go out like this morning, it was still pretty icy when I went to the gym this morning. I step out of the car and my foot just goes whoosh. Well, if you don't have friction, you can go like this all day long, but you don't get anywhere because it's not you moving your feet, it's the ground sticking to your feet, pushing you, that makes you move. So the friction would have done the work to make me move. Of course, I had to push against the ground, so I did some work as well, and we calculate that one. So kinetic energy, energy in motion, we're not going to go through a derivation of the equation and just jump straight to the equation for kinetic energy, energy in motion, is 1/2 mv squared. Now let's make sure everyone remembers, what does m stand for? Mass. What does v stand for? Speed. The difference is the vector sign, and when you do a square, it's always speed. Right? Because velocity squared, you can't technically multiply vectors together. You can dot vectors together or cross vectors together, things that you won't learn in this class. Those are linear algebra things. So a square is never a vector. And hence, that's why I'd say speed here, because it's not a vector. I wouldn't mark you wrong on a test unless it had something about having a vector sign or not having a vector sign, that kind of thing. So kinetic energy is 1/2 mv squared. Now let's come back to talking about Daisy and me. Daisy and me are now, instead of racing up the stairs, we're just doing a race sprinting. And it turns out that I run the same speed as Daisy. If we're running the same speed, how do our kinetic energies compare? Do what? She has less. Why? Because she has less mass, I have more mass. If our speeds are the same, that speed squared is the same, then the one that has more mass is going to have more energy. So now you can take this and think about like football players. Let's suppose that you have a 180-pound wide receiver, right? They do exist. And you have a 325-pound defensive lineman. One of the things about the NFL that's different than normal life is that defensive lineman can almost run as fast as the wide receiver. If they're running the same speed, which one has more kinetic energy? The defensive lineman's going to have a lot more kinetic energy. And so kinetic energy is basically a measurement that's telling us how much damage can that thing do. Well, which one can do more damage to you, the 180-pound wide receiver or the 325-pound defensive lineman if they're both running at top speed? The lineman. He will run through you, right? And that's because he has more kinetic energy. Now, we will talk about momentum soon, and we'll talk about momentum as a measurement, of like how hard it's going to be to stop the person. The two are similar in concept, but different mathematically. So things that are faster have more kinetic energy, and things that have more mass but the same speed have more kinetic energy. Now, let's suppose, take somebody here that is closer to half my weight, since Daisy is clearly too low. Let's say that Joseph and I are running, and that Joseph has exactly half of my mass. If he's going to have the same kinetic energy, that is, if he's going to be as scary as I am, how does his speed have to compare to mine? Just what? It's actually not twice as big. What'd you say? 1/4. Not 1/4. His speed squared is going to have to be twice as big. And so his speed has to be 40% larger, but basically. Square root of 2 is 1.41. So he would have to be going 41% faster to be as scary as I am. That is, if you have to stop one of us, you should choose him unless he's going more than 40% faster than I am. Right? Because I will be carrying more kinetic energy because of my mass. And I could probably go the same speed as Joseph for the first 10 meters. After that, I give up. He wins. Okay. I've already said this. I just put this slide in to make sure that we have it somewhere recorded. Yeah, we did say that a force that is in the opposite direction of the distance moved is going to make a negative work. And here is an important thing that I didn't mention on the previous slide. Just a tiny equation at the bottom, but a super important concept. The work relates to change in kinetic energy by the work is equal to the change in kinetic energy. And now I'll actually put down here the network. Why the network? Because if I have two things that are doing equal work and one's positive and one's negative, so they add up to 0, well, that's not going to change kinetic energy. But if you have a network that's not 0, the kinetic energy is going to change. And so this relationship gives us the force times the distance is equal to, remember, one change in is always which one minus which one. Blank minus blank. When I do a delta, the change in, it's always, so this is change in kinetic energy, so it's going to be kinetic energy at one time minus kinetic energy at the other time. Which one is the first one? It's always blank minus blank. So kinetic energy blank minus kinetic energy blank. What? Final. Yes. It's always going to be the kinetic energy final, so that's 1/2 mass times speed final squared, minus the kinetic energy initial. Now, if you look at my equation compared to, compared to the one at the bottom, what's different? This minus sign is specific to that problem where the force was the opposite direction from the distance. Mine was assuming force and distance are the same direction. If they're opposite directions, you have to put a minus sign. What if the force is perpendicular to the distance? Then there's no work, and hence we'd have no change in the velocity from that. So that's kinetic energy. And then we'll talk about potential energy. Potential energy is energy that's stored and can do work. So work caused a change in kinetic energy, or, remember I said we could say work is a change in energy as a definition. It really kind of goes the other way. Energy is the ability to do work. And so if something has kinetic energy, it has the ability to do work because it's moving. So if I'm running along and I come and hit Colby, I do work on him. I put a force on him, and what happened? He moved. So I did work because I had that kinetic energy. Potential energy is the ability to do work because of position. And the most common one we talk about is gravitational potential energy. We know that if I take this mass and hold it up here, if I let go, what's going to happen? It's going to drop. Okay, so before this, we talked about things in terms of forces. We said there's a force of gravity, and that force of gravity, by Newton's second law, is going to make it have an acceleration of 9.8 meters per second squared downward. Now we're looking at a different way to explain the same thing. So we say that when it was up here, there was a gravitational force acting on it, but I was keeping it from moving. When I stopped keeping it from moving, that gravitational force acted and made it move, and so that gravitational force did work on it. And that work was equal to the force of gravity, mg, multiplied by the distance it dropped, the change in height. And so we define a gravitational potential energy due to gravity, is equal to the force of gravity, mg, times the potential height it could drop, h. Now, a big question is, how do we define that potential height it could drop? And the answer is real simple. You just choose. I could say that potential energy a height is 0 right here. If it falls down 1 meter, what is its height if it's fallen down 1 meter and it started at 0? Negative 1 meter. And so the change in potential energy would be mass times gravity times the final height, which is minus 1 meter, minus mass times gravity times initial height of 0. It'd be minus mgh, because the height, or minus mg times 1 meter, because the change in height was minus 1 meter. If I set the 1 meter, up here is 1 meter, and it comes down to 0, then I would just had the final is 0 minus the initial of mg times 1 meter. And I have the same thing for the change in potential energy. It's only the change that's important. So this h you set arbitrarily to make your life simple. Arbitrarily. I suppose that's right. In a few minutes, we're going to have Michaela come up and do a little demonstration. And she's going to be doing her demonstration with this. Now, it was supposed to be with the bowling ball, which is right here. But I couldn't find my little S-hook that I used last week. And so I tried a different thing, and then I let it bounce off my chest, because I'm being a man that way. And the hook didn't hold. When it hit my chest, it popped off and fell and broke the hook off. So that's why we have this mess. So she will be doing a demonstration with this, and we'll be talking about the potential energy and the kinetic energy. It's the bowling ball. And I thought somebody was out there playing with me there for a minute. Okay, so she's going to be dealing with this pendulum, and we have to say, well, what's the potential energy at this position? What's the easiest answer for that? The easiest answer is to say, let's set that as a height of 0. So the potential energy there is 0. And then if I raise it up here, it's gone up, let's say, 1 meter, so its potential energy is mass times gravity times that 1 meter. That's the most convenient, and so that's what she's going to use when she does her demonstration. So it doesn't matter what you use as your reference, as long as you're consistent throughout the problem, it'll work out fine. because everything that we do has to do with the change in energy. Okay, so this picture here is showing a girl pulling a box up. She has to apply a force. She does work because she applies that force and she pulls at a certain distance. She's doing that against gravity. And so gravity is doing a negative work. Gravity is pushing down and going the same distance. Or we can say she changed the potential energy of the box equal to the amount of work she did. Now, I believe, we have this question. I don't think I have the spring next. I think I have Michaela next, but we'll see. So question. Work is done on a large crate to tilt the crate so that it is balanced on one edge rather than sitting squarely on the floor. Has the potential energy of the crate changed? Options are yes, it increased, no, or yes, it decreased. Okay. 8 people said yes, it increased. 1 person said no, it decreased. I think it's, actually, we can't just take the majority and say, I think it's clear they're right, because we had the situation earlier today when the majority was wrong. Okay, the equation for potential energy is mgh, where h is the vertical height. Nothing to do with horizontal, just the vertical height. So we just look at this and we say, did the center of this thing move up or down? It would have been, it would have been like this with the center here. And so it moved up that distance. And if the center of mass, the center of mass is the place where we can treat all of the masses acting. And for a uniform object, it'll be at the center geometrically. If the center mass moves up, what happens to mgh? It goes up. And so the potential energy had to increase. This is unstable. Even if it's perfectly balanced, it's unstable because if anything like a fly lands on it, it will tip one direction, and what's going to happen to the potential energy? It's going to go down no matter which direction it tips. So it's balanced when the center mass is directly over the support. And then if it tips to your right, it's just going to keep falling. The potential energy will keep dropping. If it tips to the other direction, the potential energy will drop until it's flat, but then it'll continue going and tip up the other way, and it'll just go back and forth rocking and find what we call a stable equilibrium. A situation where the potential energy is as low as it can get. You displace it either way. If you tip it either way, the potential energy goes up because the center mass goes up. So that would be a stable equilibrium. And that is like the example I gave last class period. If I'm standing like this, it's a stable equilibrium. If somebody comes and pushes me to tip me over, they first have to lift me up by about 3-4 inches. And since I weigh a lot, it's going to take a fair amount of energy to tip me up, and so it's reasonably stable. Whereas if I was on one foot, if I tip a little bit, my potential energy is just going to go down, and down goes Tyson. Right? You guys are probably all too young to have heard that, right? Buster Douglas. Okay. It was one of the greatest upsets ever in boxing, I think, because Buster Douglas was just this fat dude that everybody thought had zero chance of winning. And he got a shot in on Mike Tyson, and it's the end. Okay. She raised up that box. Why? Because she wanted to break the coconut. She did not have the ability to break the coconut with her bare hands. But she could do work over time to lift that box up, and then she lets go. And what does the cracking? What's going to happen when she lets the box drop from that position? In terms of energy, What type of energy does the box have if it's sitting up here stationary? Has gravitational potential energy. There are different kinds of potential energy. That's why I said gravitational. But when it starts dropping, what's happening? It's starting to have kinetic energy because it's starting to move. And kinetic energy is energy in motion. But where's the energy coming from? It's coming from the work done by gravity. And so that potential energy in gravity is dropping and being converted into the kinetic energy. So it starts up here with energy equal potential energy. It ends up, when it hits the coconut, with energy equal to kinetic energy. And so it transfers energy back and forth. One of the fundamental rules in physics is that energy cannot be created or destroyed. We can't use up energy. That's good, right? But we can't create energy either. All we can do is use energy. And so we have to have energy that's usable to use it. So something like a fossil fuel. We can use chemical reactions to make the fossil fuel go from a higher chemical potential energy to a lower chemical potential energy and give us thermal energy in its place. So we didn't create energy. When you burn gasoline in your car, you're not creating energy. You're converting energy from a chemical potential, energy was stored in chemical bonds, into a thermal energy of all the little molecules moving. So we cannot create or destroy, we just transfer energy from one place to another. I thought he was writing me a note because he used such big letters. Now, other kinds of potential energy, the elastic potential energy in a spring. Springs, I believe we already discussed that springs have a force equal to K times the amount they're stretched. And so if you stretch a spring, you did work, right? And since you did work, and the spring will give you back that energy, it will spring back to its initial position, it's storing the energy, and we say it has potential energy. So here's a graph showing the storing of energy on a spring. So this axis is force. You see the kx there. This axis is the distance stretched. And the energy that it stores is the area under that curve. Well, that's a triangle. The area of a triangle is 1/2 base times height. So it turns out that the potential energy for the spring is 1/2 kx squared. Now, it should be time for Michaela here. Yep, come on up, Michaela. Don't clap yet. She hasn't done it yet. Clap when she's done an excellent job.
Okay, so what is the type of energy when it's sitting here stationary? I can't hear you. It's potential energy. Okay, so what is it going to be when it, also down here, just showing potential energy. Okay, and what is it when it's in motion?
Okay, so at the bottom it was all motion. So at the bottom it was all kinetic energy.
Okay, so what's our prediction for where the weight will be when I let it go and let it come back?
Will it swing back to the same height, higher or lower?
It's going to be a little lower because of air resistance.
At least that's what physics says.
At least that's what it
So now, hold up your chin. We want to make sure we're...
This is a lot scarier with a bowling ball. It's okay.
Yeah, that's true. Now, one of the things about doing this, with the bowling ball, it is more intimidating.
Yeah.
With the bowling ball, it's more intimidating. But, I start here touching my chin. I let go. I know what it's going to do. The problem is I don't know what I'm going to do. Right? I could have leaned forward. Lean forward an inch is all it takes for me to end up with a third scar on my chin. The other two are from volleyball and being really stupid with a 55-gallon barrel when I was like 6 years old. Oh, no, 5 years old, because it was one of the barrels that we used for packing when we came to America. So, I'm more proud of the volleyball one. making a diving dig on a concrete gym. The pendulum experiment here is a classical example of conservation of energy. She had potential energy when it was up by her chin. She let go, and what was happening while it was going from her chin toward the bottom? The speed was?
It's accelerating.
Okay, it was accelerating. It was picking up speed. I was putting more weight on here to try to make the thing stretch out better. I'll have to have okay, there we go. So as it's going down, it's accelerating, it's speeding up, but we have an energy associated with speed. What do we call that? Kinetic. So it starts here with all potential energy. As it falls, it's converting potential energy into kinetic energy. It gets to the bottom, and people answered wrong here. What type of energy does it have at the bottom? Just kinetic. Why just kinetic? Because we said we're going to use this for a reference of zero potential. Measure heights from there, so zero potential energy. Then what happens is it comes back up. Potential increases. Where does that come from? Loss of kinetic. Kinetic energy is converted into potential. So energy is just being moved. I'm afraid to do it like this too much. It can go like that and hit me. You know, if it's doing this action, you just can't predict what it's going to be doing when it gets to you. But it's converting energy back and forth between kinetic and potential as it swings. The total energy, if there was no air resistance and there was no friction on that hook up there, the total energy would stay constant throughout. You can see that it's not staying constant because, okay, let's see if I can get my hand to where it just touches. Okay, so about there is where it came up. Okay, I'm a bad judge. We'll have to do the chin part. Do the chin music. If it comes back and touches my chin, then it lost no energy. Uh-oh. Right. It didn't touch my chin, so it lost some energy. And you could take the difference in height, and that would tell you about how much energy was lost. Take the mass of this thing, times gravity, times the height difference for each swing. It tells you how much energy was lost each swing. And where's that energy going? Okay, what is taking it away? And let's pretend there's no friction whatsoever up there because that's harder to deal with. So what is taking it away if it's not the friction in the metal? Not gravity. Those masses are going through air. And the air has to move. And so this is hitting air molecules, making them move, and transferring the energy into the motion of the air molecules and taking it away from this. So the energy is not lost, it's just transferred into something else that has that energy. All right. All the things that we're not going to do here. I forgot I was supposed to ask this question before. Let's go ahead and answer it now just so we officially have answered it. If a pendulum is held in my chin and released, what happens when it comes back to when it comes back? Okay, 7 people said it almost hits my chin. 2 people said it will be well below my chin. Now let's look at the meanings of each of these answers. The first one, if it smacks me in the chin, what had to happen? That would have required energy going up. I said one of the fundamental laws of physics. We don't have, actually we do. Emmy Noether's theorem gives us an actual reason for it. But a fundamental law of physics is energy can't be created or destroyed. By the way, you might have heard that a fundamental law is mass can't be created or destroyed. That was believed until 1905 when Einstein proposed that mass is just a form of energy and that you can create mass or destroy mass by converting it from the mass energy into another kind of energy. And in fact, nuclear energy is just that. It's converting, if you have a nuclear bomb, you're converting mass into thermal energy. So what you start with for the mass of the bomb is greater than what you end up with the mass of the stuff after it's blown up. And the difference goes into things blowing away with energy. Okay, the second one, it just kisses my chin. Energetically, what would have that meant? Okay, so the change in energy would be 0 then. If it almost hits my chin, then what? It went down just a little. And the final one, if it's well below my chin, it lost a lot. Okay, we're out of time, so we shall stop right at this point. Have a great hump day.